Hello, everybody. I solved these questions in face-to-face tutorial, but some of my students asked me to publish them somewhere. So I think it is the best way to publish as a record. So I would like to go through those questions again, and I'm going to publish them online. Okay, now here in this question, this is algebraic question, Mathematics 1151 in UNSW. So that is the algebra section, question 22, and H represents one of the hard questions. We have DE3. These are three non-collinear points of R3. There are exactly 3 points in R3 taken one at a time with DEF. Form a parallelogram. Calculate the vector expressions for 3 points. This is the question. So since we have 3 points that we are talking about, and non-collinear means that these 3 points, they are not on the same line. Then we will, and they are going to make a parallelogram. That is what we want. This is how we organize them. So we need to look at the configuration, possible configurations with this point. If we change the points, what will happen? Okay, and one possibility is we can put the DEF in this format, or we can change DE and put the F on this side, move the F from here to here, or we can also move from E to F, this position for this position. But this one and this one, they are equivalent parallelograms, because parallelogram means that this row and this one and this one has to be equal. This is all about it. So the requirement for a parallelogram is that this vector has to be equal to this vector, and also you want this vector is equivalent to this vector. Directions are important in this case. Okay, directions are important. So if you look at this one on DE, F something, whatever it is, you can say it. From here to here, from here to here is equivalent to DE and D F something. So it is equivalent. Right? This configuration is equivalent to this configuration. Then what else we can change? I can swap the EF for positions. Then this is not equivalent to this one, and this is also equivalent to this one. So we have 3 configurations, 3 possible configurations for these 3 points. So let's put this point name to this empty point by G, and write it down in terms of the vector equations. These are the vector equations. And again, be careful with your vectors. Vectors are different objects than usual real numbers. So it needs to be emphasized. It needs to be presented with that way. So we use tilde for vectors, or we use arrow on the top. So vector notation is very important. Just reminding in a corner, either we use tilde, or we use arrow on the top, or we use bold, especially when we are writing mathematics in some, by using a LaTeX, we use the bold form. So this is why I have tilde here. Tilde is much more easier if you're handwriting. Tilde is very exact, common to use. Okay, so what we want from this parallelogram, we can do the vector additions, what it represents, what it means. We want this vector equivalent to this vector. So that will be F minus G, this minus G. This is how we write it down things in A and B. So if you have A point, if you have a B point, and if you want to write it down a vector from A to B, we write it down B minus A, right? We write the component of the b's, we minus, take away the components of a. We actually look at this thing in from an origin perspective. We looked at it from that way. This is how we do such things. You've seen such things in your lectures. Okay, this is why I have f minus g. I have f minus g, which represents this arrow here. So this one here, so this vector is f minus g. Let's do the other one with a different color. So this vector here is dE vector, represented by E minus D. And then since we would like to know how to write it down G in terms of the others, just to tidy up the equation, we have G F minus E plus D. And similar to the others, right? Same idea. So F G will be G minus F, D E, D minus E, G E will be E minus G, D F will be F minus D, and then we will figure out the G part. That will give us that will give us the solution for this question. Okay, I think this is pretty straightforward. Now let's talk about standard bases of R5. Now, these are the main part of this course, this algebra. We will work on vector spaces. The vector spaces that you're working are infinite objects. And in order to be able to handle infinite objects, we would like to understand, we would like to use a tool that we can make our calculations easier and actually doable. And the concept of bases makes us to do that. And the standard here means that every vector space has some nicer spaces, and the standard here means nicer spaces. And these R5 are really the simplest vector space that you can possibly work on. So the standard basis, and you're familiar with. This is why we would like to start with something which you are familiar with. And then when we understand what is going on, once we are familiar with the concept of vector spaces in somewhere that we are familiar, then we can talk about some other complicated vector spaces. That's what we would like to do. So let me start writing down the standard basis for R2. So this is a set notation. Standard basis of R3 is the set of E1, E2. So this is a vector, and this is a set of two elements. And E1 will be 1, 0, E2, 0, 1. You know those vectors. And with an X and Y plane, E1 is the vector, unit vector in this direction. E2 is the unit vector in this direction. What is the significance of bases is this key idea here. And for every basis it is. Every vector V can be written uniquely as a linear combinations of the basis element. So if you think about any vector, components V1, V2, it is obvious for this E1, E2 satisfying this condition because this is 1, 0, that will give you the first component, then this part will give you the second component. It is a straightforward thing. I just would like to put the vector notation there. A linear combination means real number times to the vector plus another real number times another vector. So this is a linear combinations of the vectors E1 and E2. Linear combination idea will be extended. We will study a lot more during today's course. And yeah, you need to know. You need to know what is a linear combination, what is a basis. But we will work on such things a lot more during the term. and V1 and V2 will be the real numbers. And this notation means element of, and this notation means other set of the real numbers. So this means here verbally, V1 and V2 are any real numbers. So that's what it means. Since we have, why the real vector spaces are to do something is always nice. Nicest known vector space in some sense, because it is extremely easy to extend it. And if we have a complex structures like manifolds or something, we would like to make it simple. We would like to localize, and when we localize it, we want them to look like a real vector spaces. This is something that we can do some calculations. We can we can understand with our human mind, basically. So what I'm doing here is just this is R2, and what will happen in R3. So I'm trying to extend the idea because the dimension here is 5, and here is the dimension is 2, and I will look at the dimension 3, and then we will extend this to the R5 because our idea is to list the standard basis for R5. Okay, in R3, what will happen? The standard basis, nicest basis, will be E1, E2, E3. Again, this is the set of the vectors, E1, E2, E3. And that's E1, 1, 0, 0, E2, and E3. You know those vectors. And this is a unit vector in the direction of x-axis, unit vector in the direction of y, unit vector in the direction of z. Again, it's the same idea. Every vector in this three-dimensional space, now in this three-dimensional space, your vectors are now actually three-dimensional, right? So you have, in this case, V1, V2, V3, any vector V can be written again uniquely because you have unique components, E1 plus V2, E2 plus V3, E3. That is a unique. V1, V2, V3 components coordinates are unique. Right? That's the key. And now we are ready to extend this idea to the R5. Right? So R5, we can write it down. Standard basis element for R5 is E1, E2, E3, E4, E5 set of these vectors in this fashion. And also, I can write these ones in a little bit more compact way. What I mean by that, I can rewrite this set as defined as EI, such that I is equal to 1, 2, 3, 4, 5. You might like this definition rather than writing down everything as a list. This is nice, mathematically nice language. And then where EI is the vector in R3 such that ith position is 1 and 0 elsewhere. So this is a wording way of writing down the listing of this E1, E2, E3, E5. EI, so this is the end definition as well. If you have, sorry, this is R5. This is 5. This is 5, because we would like to look at the basis on R5. It's I5. So you have 5 EIs, exactly those ones. So this is the first position, you have 1, all the others is 0. This is the second position is 1, all the others 0. And then this type of writing allows you to write it down for n-dimensional real vector space. That's the key. Okay, I think that's all I want to say for this question. Now, this question, we would like to find out 10 vectors in R10, each pair of which is 5 root 2 apart, which means the length between each pair of vectors is 5 root 2. And we would like to find out the 11th vector or more. So we want a question mark here. Now, this question is related to the one question before. In order to be able to do these calculations, we need to understand unit cube in R3. So this is a knowledge, this is an experience that we need to have in order to be able to solve this question. This is in R3, we have a unit cube. It means, so this vector here, 1, 0, 1, or this point is 1, 0, 1, and this vector here, 0, 1, 0, and this is E1, E2, E3, and this point is 1, 1, 1. We want to find out some distances. We want to sort of examine some distances. So the distance in any two vectors in R3 is just the square roots and the subtractions of the components, coordinates B. So, for example, if you want to find out the distance D1 from 0, 0, 1 to the point 1, 1, 1, this distance is basically the vector length, vector distance, usual Euclidean distance. There are other distance formulas. There are, I mean, the vector spaces, we have many vector spaces. We have many different type of distances. Distances is a kind of a measure which has a larger concept than here, but here we only have Euclidean distance. This is what we do. In Euclidean distance case, we just take 0 minus 1 square, 0 minus 1 square, just component-wise, taking away, taking a square, and then the square root will give us a distance, Euclidean distance between two vectors. Then we find root 2. We also can ask ourselves what is the distance of D2. So this vector is 0, this point here 0, 0, 0, and this point is 1, 1, 1. And then all the distances will be 1 square, 1 square, 1 square, and square root, we will get root 3. And if we looked at DE1, DE2, for example, distance from here to here, this is E1, this is E2, and we can calculate this distance with 0, 0, 0, 1, 0. So this is distance will be 1 because E1 has one position, 1, and E2 has one position, 1, but they're in different places. So this is in the first position 1, and this is in the second position 1. So E1 and E2 has different position in 1. So only twice they will have 1 if you would like to think about the n-dimensional case for the real numbers. Always that will be root 2. Always if you take any two, standard basis element in R5, in any Rn dimensional space, then this is what will happen. And let's see that. So the standard basis for R10 is E1, E2, E10. We know that just we've seen it actually, how we construct the standard basis element of the real vector spaces. If we have the 10 dimensions, we will have E1, E2, E10, and this one will be having 1 in the one position. This one will have 1 in the second position as well, 0, and so on. And then each pair has distance root 2, right? If for any ij from 1 to 10, if I different from the j, the ej will be root 2, because only ith position is 1 and only jth position is 1. All the others will be 0. So you will have 1 square plus 1 square, square root of 1 square, 1 square. That will always be root 2, right? We know all I am doing up to now for this question is preparing an understanding. I haven't started to solve this question yet. These are all preparation. So this part here, basically, you can think of this as a start of this solving this question. But up to here, all I'll represent it is the knowledge that we are getting from our lectures and from general. This is the knowledge or previous questions that the experience that we need to have to be able to solve these questions. Up to here, it is just a knowledge. From here, we start to think about the solutions of this problem. Now, this is just a guess, because the question asked me to find out each pair has distance 5 root 2. Now, with my experience, I realized that if I have 2 standard basis elements in any dimension of the real vector spaces, I will always have the distance root 2. So I need to think about other vectors and similar to standard basis vector, but I need to change a little bit of those vectors so that I will find out the 5 root 2. So this is a test. So I'm asking to myself, what will happen if I think of taking the 5ei, 5ej vectors as the vectors that I'm searching for? As a matter of fact, it works, because ith decision, 5ei, in the ith position, I have 5. In this one, 5ej, in the jth position, I have 5. Then this distance will be square root of 5 squared plus 5 squared, which is 5 root 2. That works. So each of these pairs, 5eis, have distance 5 root 2. This is what we wanted to, and this is what we found. It's perfectly fine. This was the first part of the question. These are the 10 vectors, and each pair has distance 5 root 2. Now, the second part is that what else you can do? Can you find some other vector to add this list? Now, another important point here, we look at our experience in our tree. In our tree, we have this particularly important point here, 1, 1, 1. And also, we know that this distance, together with any E1, E2, E3, has, again, root 2 diagonal distance. Maybe we can think of such a point in R10, and then again, this time our distance, we would like to have 5 root 2. We need to adjust the thinking a little bit, but this is a good vector to think about it. This is because it works in R3. And if you manipulate a little bit in R5 with respect to our question, we should be able to get other ones. Okay, then that's what I'm doing here. So this is 1, 1, 1. And I'm multiplying with A because I'm not sure what the A should be. And A is any real number in this case. A is any real number. It's just a general A, I am thinking, because we don't know exactly. Just any real number A. Now let's taste it. What do you mean? Because we have this list of vectors, 5eis. These are the 10 vectors, and each pair has distance 5 root 2. Now we have another vector, and let's have a look. Distance of these vectors together with this particular vector, because in the question it says it should be 5 root 2. And let's have a look at this calculation. So this is so here only the jth position is 5, right? So you have these vectors. You have the vector A, and you have the vector 5 in jth position, and then zeros elsewhere. So you're looking at the distance between these two vectors. So you have A everywhere. So for the ijth position, so you have only A minus 5, or 5 minus A squared. So this is this part. This is this part. But for all the other parts, I have only A squared, right? A squared, except this one, A minus 5 squared, and all the others A. So I have 9 of them, 9 of the A squares, and one of them will be A minus 5, which is the jth term. And then we have the square root of 9A squared plus A minus 5 squared. The requirement is what we want. This distance is equal to 5 root 2. Which means that this equality is 5 root 2. So taking the square on both sides, we have 9A squared, A minus 5 squared is equal to 50. So this is the equation that needs to be satisfied. So for any A, satisfying this equation can be the can give us the 11th vector. And the 11th vector, we can define A is I is equal to 1 to 10, EI, that will be the 11th. Actually, it is the 4th because you will have 2 roots in here. I think I want the give, I think is a good word there. Any A in the real number satisfying this condition can give the 11th vector. This is the this is a sensible choice to do. And why it is sensible? Because we looked at the R3 case and we realized that this point is special. This point is special in that sense. And we would like to apply this idea in R10, right? This is 1, 1, 1 vector is basically a sum of all standard basis element. If you add all the standard basis element, since each position is 1 for each of those basis vectors, and when you add them, then you will have the vector 1, 1, 1, 1. You multiply by any element in R. That will give you a flexibility for solving this question. Then you looked at the distance between these 10 vectors and then this particular vector. And then you figured out an equation. And once you solve this equation with respect to the A, you will have 2 roots. So the 12th vector that you find is a bonus for you. That's all. Thank you very much. I hope these solutions are useful.